Hello, welcome to the course PH5 BO6 Electrodynamics 2. Today we will start Module 4, Alternating Current Circuits. The contents of this module is taken from Chapter 22 of Fundamentals of Magnetism and Electricity by D.N. Vasudeva. Now, before going into the details of AC circuit, let's first try to understand the fundamental difference between alternating current AC and direct current DC. So these are the waveforms of a DC signal and an AC signal. Typically, the most common source of a DC signal is a battery. If you take a battery and connect it to a multimeter, you will find that multimeter shows a constant reading. For example, if you take a 12-volt battery, consistently the multimeter shows a 12-volt reading, which means the amplitude of the signal is a constant. And if you look at the direction of charge flow, always electrons leave the negative terminal and move towards the positive terminal. So electron flow is in the counterclockwise direction, but by convention the current flow is taken in the opposite direction of the electron flow. So current flow is always in the clockwise direction in this figure. So in other words, in the case of direct current, amplitude and direction are constants. On the other hand, if you take an alternate current, you will notice from this figure that the amplitude changes as a function of time. But the change is not random, this is a periodic change. And if you look at the direction of the signal flow from this diagram, you can make out that half the time it flows in one direction and the remaining half it flows in the opposite direction. We can illustrate this with an example of water movement through a pipe where the flow is controlled by a piston movement. So there is a rotating wheel which is connected to a moving piston through a crankshaft, and you can make out from the figure that when the piston moves to the extreme left, water flows in the counterclockwise direction, and when the piston moves towards the extreme left, water flows in the clockwise direction. And here there is a narrow patch which offers some kind of resistance to the water flow. So this acts as a resistor here. And if you monitor water flow through the resistor, you can see half the time water flows in one direction and the remaining half it flows in the other direction. So this is what we mean by an alternating flow. So in the case of alternate current AC, the amplitude and direction change periodically with time. Even though I have plotted a sinusoidal signal here, as we have discussed in one of the previous classes, the waveform need not be sinusoidal. It could be square, triangular, anything, but usually we represent wave using a sinusoidal function because this is the most fundamental waveform using which you can construct any other wave type. And if you are still wondering why does the amplitude and direction of an AC signal change periodically, this is because of the peculiar nature of AC production. So typically, alternating current is produced using what is known as an alternator. So alternator consists of a conducting loop which is connected to a turbine. So when turbine is rotated using some kind of force, usually it is done using the kinetic energy of moving water or the force from winds or force from steam, etc. So using some mechanical force, when you rotate the alternator, what happens is this loop is kept inside a strong magnetic field, and the blue lines here indicate the direction of the magnetic field. So as you can notice, when the loop is along the plane of the magnetic field, the flux through the loop is zero, and when the loop is perpendicular to the magnetic field, the flux through the loop is maximum. So when it rotates, Basically, the flux through the loop changes periodically, and because of electromagnetic induction, this produces an EMF. As the flux change is periodic, the resultant EMF is also periodic. Now, if you are interested, you can do a homework. This is some kind of a survey. So basically, you make a list of all the appliances, both electronic and electrical appliances used in your home, and categorize them into DC appliances and AC appliances. Now, some of you may be wondering, like, the power supply in our home is an AC power supply, right? Typically, it's around 230 to 240 volt at 50 hertz. In 1 second, it changes 50 times. And all the appliances in our home are connected to this AC power supply. So we may be thinking that all the appliances are AC appliances, but that's not the case. For example, if you take the LED, which is used for lighting in your home. If you open the LED, you will find that there is a rectifier circuit inside. So even though we are connecting LED to an AC supply, inside the LED, AC is converted into DC, and the LED works through this DC supply. So in essence, LED is a DC appliance. Similarly, if you take your laptop computer, once again, it's connected to an AC supply, but if you look at the charger, it has an AC adapter. Once again, the adapter converts an AC signal into DC signal. So your laptop is also a DC appliance. Similarly, if you take your phone or tablet, they all work using a battery, and battery is a supply of direct current, so they all are DC appliances. On the other hand, if you take your refrigerator or air conditioner or the iron box, they all are AC appliances. So you can make a list of DC versus AC appliances, and you will find that majority of the instruments, especially the electronic instruments, they come under the DC category. So even though most of our requirement is related to DC, why is it that we still have an AC power supply? Because it makes more sense to have a DC supply using which you can directly power all the DC appliances, right? There are several reasons for this, why AC is preferred over DC. The three major reasons are listed here. First one is the generation. There are several methods for producing AC and DC, but if you look at the mass production of electricity, this is highly favorable towards AC. So if you look at our hydroelectric power stations or wind power station or thermal power station, what they all do in hydroelectric power, using kinetic energy of moving water, they rotate a turbine, and once the turbine rotates, it activates an alternator which produces AC electricity. Similarly, in the case of wind, the power of air current is used to rotate the turbine. Similarly, in the case of thermal power plant, the force of the steam is used to rotate the turbines. In all cases, an alternator is activated using some kind of mechanical energy, and using that electricity is produced. So as we said, alternator fundamentally produces an AC signal. So because of that, all mass production methods of electricity is related to AC power. We also have DC power generation method like chemical cells and solar cells, etc., but they cannot produce electricity in a mass scale. So in generation wise, AC is preferred over DC. Secondly, the transmission. So if you look at the power grid, so power is generated, or electricity is generated at the power station, and the electricity is not given directly to your home. So before that, what they do, using some kind of stepping up technology, they increase the voltage. This is known as step up. Then before giving the electricity to your home, they once again reduce the voltage. This is known as step down. Okay. So if you look at the transmission grids, major transmission grids, the voltage level is usually very high. This is of the order of 100 kV or more. So you have 100 into 1000 volts here. So why do we need very high voltage for electrical transmission? We all know that whenever electricity passes through a conductor, because of the inherent resistance of the conductor, a part of the electrical power is lost in the form of heat. This is known as Joule's heating or heat dissipation. If I is the current through the conductor and R is the internal resistance of the conductor, then the power loss is given by I square R. So from this we can make out that if the current is more, the power loss is going to be more. So if you want to reduce the power loss during electrical transmission, you need to decrease the current as small as possible. Okay. So you know that power P is given by voltage into current. So if you want to decrease the current, you need to increase the voltage. So that power P remains a constant. This is the conservation principle, right? So using some step-up mechanism, you increase the voltage as high as possible. Consequently, the current becomes very low. Thereby, you can decrease the transmission loss. Now, how do you step up or step down the voltage level? One of the common methods is to use a transformer. So a step-up transformer increases the voltage level, and a step-down transformer decreases the voltage level. So this is the most cheap and robust method of stepping up and stepping down. Unfortunately, transformer works only with AC signal. We know that, right? Because this works by the principle of electromagnetic induction, so it can deal only with AC signals. So once again, in the transmission side also, AC is preferred over DC. Finally, coming to the user end. Even though in our household applications, DC instruments are more compared to AC, if you take the total user end, majority of the electricity produced is used in the industry. And in industry, for any mechanical work, we use a motor. And there are two types of motor, AC motor and DC motor. But an AC motor is a more cheap, robust and simple method of producing mechanical motion over a DC motor. That's why in industry predominantly they use AC motor or induction motor. So in the user end also AC is preferred over DC. So if you look at the generation, transmission and reception, in all the three stages AC is more favored over DC. So that's about some of the differences and comparisons between an AC signal and a DC signal. Let's now get into the business of analyzing an AC circuit. Whenever you are analyzing an AC circuit, the fundamental question you are asking is either for a given applied AC voltage E equal to E naught sine omega t, what is the corresponding current flowing through the circuit? Or you can ask the converse question, to produce an AC current I equal to I naught sine omega t in the circuit, what should be the applied voltage? So this is what we mean by AC circuit analysis. For a given voltage, what is the current? Or for a given current, what should be the voltage? Now there are three major methods for analyzing an AC circuit. First one, as we have done in the previous module, identify what are the various voltage components, write down the EMF equation and solve it. We are already familiar with this method. Second one is a graphical method where you draw a vector or phasor diagram and solve it using some geometrical methods. Third one is a J operator method. So we'll have a flair of all the three in our coming classes. As a starting point, let's take the simplest case, an AC power supply connected to a single ohmic resistance. So as always, we are going to consider a sinusoidal signal. E equal to E naught sine omega t, where E naught is the peak voltage, omega is the angular frequency, and omega t is known as the phase term. So you have connected an ohmic resistance to an AC power supply. So what happens? This power supply is going to drive current through this circuit. Assume that I is the instantaneous value of the current. When the current flows through the resistance, a potential drop is going to happen across this resistance, called that as VR. If I is the current, R is the resistance, potential drop across the resistor VR is equal to IR. Since we have only a single resistor in this circuit, the entire applied voltage E is going to drop across the resistance. So you can write potential drop VR equal to E. From this you can write the instantaneous value of current I equal to E by R, expand E in terms of E naught. This is E naught sine omega t by R. Now what is this term E naught by R? E naught is the peak voltage, R is the resistance. Voltage by resistance is current. So peak voltage by resistance is peak current I naught. So you can write I equal to I naught sine omega t. Let's plot voltage and current as a function of the phase omega t. So the blue line is the voltage and the red line is the current. So you can see when omega t equal to 0, sine 0 equal to 0. So both start at the 0 position. This is the origin, and it gradually increases at omega t equal to 90 degrees, sine equal to 1. So voltage reaches the peak value E naught, current reaches the peak value I naught. Once again at 180 degree or pi radians, both become 0, and when the phase is 3 pi by 2, the sine function becomes minus 1. So the value is minus E naught for voltage, minus I naught for current. Once again at 2 pi, both becomes 0. So you can notice that both voltage and current, they rise simultaneously, they also fall simultaneously. In other words, voltage and current in the case of an ohmic resistance are in phase. In the next class, we will discuss AC through an inductor and also AC through a capacitor. Thank you.